Have you ever wondered if wormholes could be a shortcut for interstellar travel? Our universe is an unfathomable expanse of celestial wonders. Its vastness is so immense that our minds, bound by earthly experiences, struggle to comprehend its magnitude. Yet, we humans are relentless in our thirst for knowledge and exploration. Since time immemorial, we have looked up at the night sky with wonder and curiosity, a yearning to understand and explore the cosmos echoing in our hearts. The universe, in all its glory, is a cosmic ballet of galaxies, stars and planets, all dancing to the tune of the laws of physics. These celestial bodies are scattered across the universe, separated by distances so enormous that they baffle the human mind. If we were to travel to even the nearest star using conventional means, it would take us over 40,000 years. So how can we ever hope to explore the universe? Well, necessity is the mother of invention, and our need to traverse these astronomical distances has given birth to a plethora of theories and ideas. Some of these theories are based on technology that we currently possess, like building faster spaceships or harnessing the power of nuclear fusion. Others, however, delve into the realm of theoretical physics and require us to rethink our understanding of the universe itself. That's where the concept of wormholes comes in. Wormholes are a theoretical solution to this problem, a potential shortcut through the fabric of space-time, allowing us to reach distant parts of the universe in a fraction of the time it would take using conventional means. They are not merely a figment of science fiction, but are a serious scientific proposition rooted in the laws of physics. One such theory that has captivated the minds of scientists and space enthusiasts alike is the concept of wormholes. This fascinating concept, nestled within the complex world of theoretical physics, could be the key to unlocking the mysteries of the universe and making interstellar travel a reality. But what are wormholes, and how do they work? Let's delve deeper into the rabbit hole, or rather the wormhole. So what exactly are wormholes? Let's dive into this intriguing concept, shall we? You see, wormholes are theoretical passages through space-time, predicted by the principles of general relativity. These principles, proposed by Albert Einstein, suggest that space and time are interwoven into a single four-dimensional fabric. This fabric can be curved and distorted by massive objects, like stars and planets, creating what we know as gravity. Now imagine pinching that fabric, folding it in half, and then poking a hole through both layers. You've just created a simplified model of a wormhole, a shortcut through space-time. It's as if you've folded a map so two distant points touch, allowing you to step directly from one to the other. That's the magic of wormholes. In the context of the universe, wormholes could potentially connect two distant regions of space, or even different universes altogether. They could also connect different points in time. A trip through a wormhole could be like stepping into a cosmic elevator, pressing a button, and stepping out light years away from your original location, or even in a different era. However, it's crucial to remember that wormholes are still purely theoretical. While the mathematics of general relativity allows for their existence, we have yet to find any physical evidence that they are real. They exist in the realm of the unobserved, the untested, and the deeply mysterious. But let's indulge in the possibilities for a moment. If wormholes do exist and are stable enough to traverse, they could revolutionize the way we travel through space. No longer would we be bound by the vast distances between stars. Interstellar travel would not mean years or decades of journeying through the emptiness of space. Instead, we could step through a wormhole and emerge on the other side of the galaxy in the blink of an eye. In theory, these cosmic shortcuts could drastically reduce the time taken for interstellar travel. But as with all things in science, it's not quite that simple. And we'll explore why in the next scene. The root of wormhole theory lies in the work of two brilliant physicists. Albert Einstein and Nathan Rosen in 1935 came up with a solution to the equations of general relativity that led to the concept of a bridge through space-time. This bridge, now known as the Einstein-Rosen bridge, could theoretically connect two distant points in the universe, much like a tunnel might connect two distant cities on Earth. The Einstein-Rosen bridge proposes that the fabric of space-time, the four-dimensional structure that Einstein described in his theory of general relativity, can be curved and twisted in such a way that a shortcut, or wormhole, is created. This shortcut could potentially allow for faster-than-light travel between 2 points in the universe. To put it simply, imagine folding a piece of paper in half and then pushing a pencil through it. The pencil's path represents the wormhole, providing a direct route through an otherwise long journey. However, the Einstein-Rosen bridge isn't without its caveats. The original model predicted a wormhole that would collapse too quickly for anything to pass through, a detail that poses a significant challenge for any would-be interstellar travelers. Moreover, the theory also suggests that these wormholes would be microscopic, far too small for a spaceship to pass through. And even if we found a way to enlarge them, keeping them stable is another hurdle. They would need exotic matter, a type of matter that is not yet fully understood by scientists and is thought to have negative energy density, to keep them from collapsing. The Einstein-Rosen bridge gives us a tantalizing glimpse into the possibilities of space-time manipulation and interstellar shortcuts. It presents a theoretical basis for the existence of wormholes and, by extension, the potential for faster-than-light travel. While the theory is fascinating, the practical application of it is another story. But as we delve deeper into the mysteries of the universe, who knows what we might discover next? Harnessing wormholes for space travel is far from a simple task. Indeed, the challenges are many, and each presents its own unique set of problems. First, we need to discuss the instability of wormholes. In their natural state, wormholes are incredibly volatile. They open and close in the blink of an eye, far too quickly for any spacecraft to pass through. To keep a wormhole open long enough for a spacecraft to travel through, we would need some form of exotic matter. This is not your everyday matter. This is matter with negative energy density, something we've never observed directly in the universe and have only theorized about. And it's not just about finding this exotic matter. We would need to understand how to manipulate it to stabilize a wormhole. In essence, we would have to become master architects of the universe, able to bend and shape its very fabric to our will. This is a challenge that makes climbing Everest seem like a stroll in the park. Then there's the danger of singularity. You see, a wormhole is, in essence, a black hole with a back door. And as we know, black holes are not exactly friendly to anything that ventures near them. They have a singularity at their heart, a point of infinite density and gravity that can rip apart anything that comes near. If a wormhole has a singularity within it, any spacecraft attempting to travel through could be torn to shreds. And even if we overcome all these challenges, we still have to deal with time, because wormholes could potentially connect not just two different points in space, but two different points in time. And that opens up a whole new can of worms, from paradoxes to the possibility of altering history. Overcoming these obstacles is a monumental task for scientists. But as we've seen throughout history, monumental tasks are not insurmountable. They simply require the right combination of ingenuity, determination, and a dash of daring. Despite the challenges, the scientific community isn't giving up on the possibility of wormhole travel. They're focused on finding potential solutions to overcome the hurdles that currently stand in the way of this revolutionary mode of transportation. One such solution centers around the use of what's known as exotic matter. This isn't your run-of-the-mill type of stuff. Exotic matter is thought to possess negative energy density and large negative pressure. These properties could potentially stabilize a wormhole, preventing it from collapsing in on itself, which is one of the major issues we've discussed earlier. Now, let's pause for a moment. Exotic matter sounds quite, well, exotic, right? But it's not as far-fetched as it might seem. In fact, scientists have already observed phenomena that suggest the existence of such matter. For instance, the Casimir effect, a quantum mechanical phenomenon, hints at the presence of negative energy densities. However, it's not just about keeping wormholes open. Another challenge is avoiding singularity, the point of infinite density in a wormhole that would rip apart anything trying to pass through. This is where the concept of a charge-neutral wormhole comes into play. The idea is to balance the positive and negative charges within a wormhole, theoretically negating the destructive effects of singularity. But it's not all about exotic matter and charge neutrality. Some scientists suggest that we might not need to physically travel through wormholes at all. Instead, we could send information through them, leveraging quantum entanglement, a spooky phenomenon where particles become interconnected no matter the distance separating them. Of course, these solutions are still in their infancy, and there's a long road of study and experimentation ahead. but they represent intriguing possibilities that could one day make wormhole travel a reality. Who knows? We might just be on the cusp of unlocking the secrets of the universe. While these solutions are still in the realm of theory, they represent a beacon of hope for wormhole travel. What does all this mean for the future of interstellar travel? Imagine, if you will, traversing the vast expanse of the universe in the blink of an eye. No more decade-long journeys to the nearest star system. No more generations of astronauts born, raised, and passed on within the confines of a spaceship. This is the potential promise of wormhole travel, a revolution in space exploration. Successful wormhole travel would be akin to finding the ultimate shortcut. It could turn the seemingly impossible voyages into manageable trips. The farthest reaches of the universe, the most distant galaxies, the most exotic cosmic phenomena, all within our grasp. It's like being given a key to the grand cosmic library, with all the secrets of the universe waiting to be uncovered. Beyond the realm of exploration, consider the potential for human colonization. With wormholes, we could spread our wings, not just within our solar system, but across the entire galaxy. The human race could become a truly interstellar species, with homes on countless worlds, each one a testament to our indomitable spirit and unyielding curiosity. But let's not get ahead of ourselves. The reality of wormhole travel is still confined to the realm of theoretical physics and sci-fi fantasies. There are hurdles to overcome, from understanding the true nature of wormholes to figuring out how to create, stabilize, and navigate them. It's a daunting task, yes, but one that could reshape our understanding of the universe and our place within it. So we stand on the precipice of a new era in space exploration, an era that promises to test our scientific prowess, our technological capabilities, and our very understanding of the cosmos. We must continue to push the boundaries of what's known and venture into the unknown, all in the pursuit of knowledge and discovery. The prospect of wormhole travel is a thrilling, albeit challenging frontier in our quest to explore the universe. The journey to unlocking the secrets of wormhole travel is a long one. We began this exploration with the mystery of the universe, and in our quest for understanding, we found ourselves standing at the mouth of a wormhole. These fascinating phenomena, first proposed in the context of the Einstein-Rosen bridge, are like cosmic shortcuts, theoretically allowing us to traverse vast interstellar distances in the blink of an eye. Yet, as we've uncovered, wormholes are not without their challenges. Their unstable nature, the enormous energy required to keep them open, and the potential dangers of traversing through them. These are not easy hurdles to overcome. They are challenges that demand our best minds, our most advanced technology, and our unwavering commitment to exploration and discovery. But despite these challenges, the potential rewards of wormhole travel are simply too great to ignore. Imagine being able to step through a doorway and find yourself on the other side of the universe, or even in a different universe entirely. The implications for space travel, for our understanding of the cosmos, and for our very place within it are staggering. And so, we continue to push forward, driven by our innate curiosity and our unyielding desire to explore the unknown. We continue to search for solutions, to imagine new possibilities, and to dream of a future where the stars are not just points of light in the night sky, but destinations within our reach. While the road is long and the challenges are many, the human spirit of exploration and discovery continues to push the boundaries of what's possible. Who knows? Maybe one day we might just find ourselves stepping through a wormhole to another part of the universe,